Okay, we're going to go over part 2 of the midterm review. Name 4 properties of a metal. We're starting off at number 37. Malleable. That means you can sort of bend it. It's pliable, similar to a spoon. You can bend a spoon. The next one, ductile. What ductile means is able to be drawn through wire. Can anyone list another property of a metal? A good conductor. Good job. Generally, they're shiny as well. Number 38, draw the correct Lewis dot structure for NaCl. As soon as you see Lewis dot, you should think 2 things. Dots, and then valence. Okay, so for NaCl, you draw the number of dots at however many valence electrons there are. So for Na, you have to look at your periodic table. The valence electrons are 1. 1 dot for Na. Cl, the valence electrons are 7. Okay, it's for the whole group or the whole column. 7, 6, 5, 4 valence for the whole column. Okay, so if you have your colorful periodic table, that will assist you throughout the midterm. But you have to do all 3 parts of the midterm review. For chlorine, it's 7. 1, 2, 3, 4, 5, 6, 7. Okay, that's the Lewis dot structure for NaCl. Number 39, the model for predicting the shape of a molecule that's based on the repulsion of electrons for each other is VSEPR. Okay, VSEPR, we learned this, and it was also called molecular geometry, when we went to the computer lab and messed with the 3-dimensional shapes, okay, the stick and ball models, and you moved things around and you could see the degrees. That's what it's talking about right here with VSEPR. 40. Draw the Lewis structure for water. Okay, there wasn't a whole lot of room. I'm going to have to zoom out. I'm just going to do 40 right here. So for water, as soon as you hear Lewis dot, you should think about dots and the valence. So what's the valence for hydrogen? 1. Again, valence is at the very top of the group. Here's hydrogen. 1 valence electron. The valence is the outermost shell. So whatever's on the outside, that's the valence. The outside of the electron cloud. Oxygen, what's the valence for oxygen? Anyone? The valence electrons for oxygen? Here's oxygen.
6.
There's 1 for the hydrogens, and then oxygen has 6 dots. And then I want you to draw the shape. Okay, and that shape is called bent. For water, you're just going to have to memorize it. And we should be familiar with seeing this just throughout our sciences. Number 41, a molecule has the formula AB4 and the central atom is in a different plane from the surrounding 4 atoms. The shape of 41 is tetrahedral. Tetrahedral. Don't forget, tetra means 4. And I'm going to explain that to you because there's an example on number 42. So these two are similar. When it says AB4 right here, it's just talking about as if it were CH4, some type of compound, 2 elements, okay? AB they just put as kind of a template. So let's do 42. What are the molecular geometries? When you hear molecular geometry, it's just asking you about the shape. So for ammonia, I'm going to write the answers first, and then I'm going to explain them. Trigonal, pyramidal. Okay, 42A, trigonal, pyramidal. B is linear. (42C) is tetrahedral, and water, we said, was bent. These might be a good idea to put on your index card. Just a suggestion. There is a pattern that we can spot with NH3 and CH4. I'm going to draw NH3. If you kind of connect the dots, or not the dots, if you connect the elements, it sort of looks like a pyramid. I'm going to make one more connection with the pattern, but let me do it for tetrahedral. It's CH4, so that means there's one C and four H's. Okay. The other pattern is there's one in the center, and there's three surrounding it. Tri means three. Okay, 1, 2, 3. And then the same thing for tetrahedral. One in the center. Tetra means four, and there's four surrounding it. (43) After drawing the Lewis structure of the compound PCl3, determine how many total valence electrons there are. Do we really have to draw it to know how many valence electrons there are? No. We could just look at the periodic table. Okay, a little shortcut. So how many valence electrons are there for P? Good job. 5. Okay, and you just look where P is for phosphorus, right here. Go to the top of the group. 5. Cl, what's the valence electrons for chlorine? 7. Except it says there's 3 of them, okay? Do not forget that. That's very important. Is that a subscript or a coefficient? Subscript. 7 times 3 is what? Okay, so we just do 21 plus 5. That's the total valence. Now, if you really, really, really wanted to draw it, you could. There's 3 Cls. There's 5 dots for phosphorus. For chlorine, they each get 7. And that's how you do that. 44. According to Vesper theory, the structure of the ammonia molecule NH3, they already gave us that answer. Okay, it was right here. Trigonal, pyramidal. The Lewis structure of ASH3 shows how many lone electron pairs on arsenic. Okay, so there's not much space, so I'm going to draw it below. AS, and then how many H's do we have? 3. There's a little 3 right there, the subscript. Okay, so the valence for AS, arsenic, which is right here, atomic number 33, 5. Oh, it's way at the top. Okay, so there should be 5 dots around arsenic. What's the valence for hydrogen? 1. So they each give 1. Okay, and it's asking how many lone pairs are there? You need to write this down. A lone pair consists of 2 electrons paired but not used in bonding. I'm going to zoom in a little bit. Okay, the lone pair, 2 electrons paired, but it's not used in bonding. So these 2 are paired up here, but are they being used to be bonded to anything? No. So you have 1. You have 1 lone electron pair. Number 46. Draw the loose dot for NH3. Look at the valence for nitrogen. It's 5. And then H gives 1 each. So there should be 8 dots around the nitrogen, and that's the octet. It wants 8. I'm going to flip to number 47. The electrons available to be lost, gained, or shared when atoms form molecules are called what? What are the outermost electrons called? Valence. Good job. A chemical bond resulting from the attraction between a cation and an anion is called what? Is a cation positive or negative? Positive. Exactly. Cats have paws. And an anion is negative. Therefore, this question is asking the same thing if you were to put together a metal and a nonmetal. Again, because it says, what kind of bond comes from a metal and a nonmetal? Is that ionic or covalent? Good job. 49, the electron configuration for aluminum, atomic number 13, is in period, what period? So, what period is aluminum in? I'm going to look at my periodic table. I'm going to have to zoom out to get it. Where my finger is where aluminum is. Okay, right here. This is period 1, period 2, period 3. Okay, period 3. 50, hydrogen gains stability as the H2 molecule by forming the noble gas configuration of helium. Oh, I have to go back to 50. That was for 51. Sorry. So now let's go to the true 50, the real 50. The elements whose electron configurations end with S2 and P5. So it's just saying belong to what group. Okay, the groups are the ones at the top. It says it goes to, it ends in P5. So if we were, this is the entire P block. 1, 2, 3, 4, 5. That's P5. Okay, so anything that ends in P5 is going to be in group what? 17. Okay, I really want you to pay attention to number 52. Okay, it's a two-step process and we're going to have to butterfly. Draw the diagram that correctly represents the formation of magnesium fluorine. Magnesium and fluorine. The charge for magnesium is what? And the charge for fluorine is -1. So you're going to have to drop this down, okay? Because you're going to have to draw a diagram of what this looks like. So it's MgF2. Okay, and that's really important to do that step first, because when you draw it, if you didn't do that step, you're going to be looking just for a picture with one fluorine, because you read magnesium fluorine, so you would just look for an Mg and an F. That's why you have to butterfly it, because there's two fluorines. So when you look at the picture, how many fluorines do we need to see? 2. Okay, so Mg, F, F. So we're going to get the valence electrons for magnesium. That's going to be 2. And for fluorine, it's 7, so put 7 dots. And do it for this fluorine too. Really quick, we need to remember and go over this. Ionic equals stealing. Write that down. Covalent equals sharing. This is going to be a nonmetal and a metal, and this is a nonmetal plus nonmetal. So with magnesium and fluorine, is magnesium a metal or a nonmetal? Everything to the left of the periodic chart is a metal. So magnesium is a metal, fluorine is a nonmetal, so it's ionic. They're not going to be sharing anything. Okay, fluorine only needs one more to get to the octet. So what's going to happen between these two, this one for magnesium will go here, and this one will be stolen to here. Stolen or given, however you want to look at it. What is the law of conservation of mass? Mass cannot be created nor destroyed. Balance the equation. For number 54, there wasn't that much space. It's the same thing. I just wrote it down on this piece of paper. So I am doing number 54 and 55 here so you can see. So you can go ahead and start balancing. See, there's one CA, CN. Are these CNs together or apart? What is going on here? Okay, the best way, or a good way to figure it out, is how is it on the product side? Do you see a capital CN together over here on the product side? No, I don't see one together. So I'm going to separate them. I'm counting these as separate. If it were together on the product side, somewhere over here, then I would keep them together, but they're not. This C is separate. One CA, one CA. One C, one C. And catch me if I make any errors. 2 ends, 1 end. Okay, so right away I need ends over here. I'm going to put a 2. By putting that 2 there, I now have 2 ends, but what did it do to my h's? How many h's do I have? 2 times 3, I now have 6 h's. Okay, over here I only have 2 h's. So I'm going to put a 3 here. If I put a 2 there, it would be 2 times 2, and I would only have 4 h's. So I just went up a number and put the 3 there to give me 6, because that's how many I need, because it gets multiplied by this. With this 3, though, it carries through everything here. So I have how many oxygens now? Okay, so I'm going to go through and see if it's even. 1 Ca, 1 Ca, 1 C, 1 C. 3 O's, 3 O's, 2 N's, 2 N's. Okay, it's now balanced. Did anybody get anything different? So the official coefficients should be 1, 3, 1, 2. And you can pause it if you need to get that down. I'm going to start at 55. The question says, what's the correct coefficient for aluminum oxide in the following equation? Okay, so 2 things. I have to go ahead and balance it. That's why I put the line here. But it only wants the coefficient for aluminum oxide. Does it want the coefficient for this? No. For this? No. Aluminum oxide, it wants the coefficient only for that. Regardless, it needs to be balanced. Go ahead and start that process. Okay, put a 2 there. Down. I have 3 here. Oxygens. 6 oxygens, so I have to put a 2 here. That 2 gives me 4 aluminums. But at the same time, it also gives me what I need with my oxygens, which is 6. Now I have more aluminums here, so I need to go back and put what number here? And at the end of the day, they only wanted the coefficient from here. So the correct answer is 2. The coefficient for aluminum oxide is 2. I'm going to go back to the worksheet. Using the equation, how many nitrogen atoms are in the product before balancing? Okay, it says product before balancing, so that's great. We don't have to balance. How many nitrogens are right here? Just 1. And that's it. Okay, so this is the end of part 2